Okay, good afternoon. Let's get working on Zener diodes. So I want to wrap up diodes chapter today. So pick up the pace a little bit. Okay. All right. I'll do a quick recap and then we'll get into analysis and examples. Okay. E6. All right. There we go. All right. So we first began looking at a voltage regulator circuit using a Zener diode. Voltage regulation uses the property of a Zener diode that it holds the voltage across its terminals constant, right? And so we first look at an ideal circuit where you're simply applying V in from the left, obtaining V out. Obviously, real life, that's not possible, right? Because a voltage source will supply its rated voltage. So we could never have V in equal to VZ without having a resistor in the middle. And so we have a kind of practical circuit where you have a series resistor. That series resistor limits the current or allows us to control the current that's coming from the power supply that causes a voltage drop across RS and R. R at the far end is your load resistor. Typically, many books would simply use L, but the book that we are using simply uses R. I actually don't like that. I like subscript notations. Anyway, the RS stands for series resistance. R or RL is for the load resistance, the far right. Okay. If you remove the Zener diode, RS and RL create a voltage divider network. It's a voltage divider network in connection with a voltage source, VS, causes a voltage drop across both resistors. And that's how the Zener diode would operate. Since the Zener is in parallel with RL, the voltage across the RL must be larger than VZ for regulation to occur. All right. So we stop right there. All right. Now, two or three things that we need to keep in mind. The load current at the far right, let's call it I or IL. Right? That's the load current that's coming from the top. So this is referred to as I or load current IL. Okay. And we have IS coming from the source, and you have IZ going down the Zener diode. So if you apply KCL at the top node, or you apply KCL at the bottom node, doesn't really matter. What do we get? We get IS, the supply voltage coming into the Zener diode and the load resistance, and IZ and IL are in parallel branches. So the total supply current coming from the power supply is divided between the Zener diode and the load. There's no other pathway for the current to go through. Okay. So essentially, all circuits can be reduced to one single resistance as the Thevenin resistance, and we can describe the entire load as one single load resistance. So total supply current coming from the supply is split between the Zener diode and IL. I mean, Zener diode and the load resistor IL. Okay. So that's first point to keep in mind. Second one, VL, the voltage at the output, is equal to the Zener voltage. They're in parallel, right? So voltage at the output, voltage at the load is equal to the Zener voltage, VZ. So VL is equal to VZ. So in general, if you look at any circuit, pretty much any textbook or any author, they will always refer to VZ and not VL. As engineers, you should automatically realize that VZ is also for the load, okay, because they're in parallel. All right, and then we can find I or IL, the load current, as simply VZ over the load resistor RL, Ohm's law. And then IS, finally, we can write an equation for IS. IS is the current that is flowing through RS. Okay. The two voltages at the two nodes of the resistor RS are VS and VZ. So there's VS at this point, and there's VZ at this point. VS, VZ. So IS can be described in terms of the difference between VS and VZ. So total supply current is VS minus VZ over the series resistance RS. These are the 4 points that you have to keep in mind. Okay, so far so good. Okay, so based on these conditions and these setup rules, there is if you're designing a practical regulator circuit using a simple Zener diode, then there is a limit on the supply voltage, meaning there's a minimum supply voltage that the circuit can handle, and there's a maximum supply voltage, as well as minimum and maximum values for the load resistance. Okay. And to take it even one step further, there's also a value for the series resistance RS. Again, you can see how all of those are interlinked. If any one of them changes, it affects the rest of the circuit. If RS changes, that affects the total supply current. If the load resistance RL changes, that changes IL, that affects the rest of the circuit. Again, so there's minimum and maximum range values for the supply voltage, the load resistance, as well as the series resistance. And determining the values of those three for a particular application is part of designing a voltage regulator, Zener voltage regulator. Make sense? Yes. So the question being asked is, could this be used more for voltage reference than an actual power supply? I would say yes and no, depends on your application. If it's like a standard application, like let's say our chargers, phone chargers and stuff, then Zener diodes are not the best. There are off-the-shelf voltage regulators that are available. They're integrated circuits, so you can just buy them off the shelf. And they have a few more components built into it. And so the answer to your question is yes and no. Depends on the application. Okay, so let's see, what was I? So RL has a minimum to maximum range, which depends on VZ. Any changes, okay, and VS also has a minimum to maximum range. So again, there's lots of variables in there. We can create a design problem using any one of those variables. I mean, in this class, we're simply applying, so we won't look at all case scenarios, but we'll look at one or two of those. So any changes in the values of RL and VS requires that the Zener diode still hold the voltage across its terminals constant. And that is known as regulation. You're regulating the output voltage, keeping it constant, irrespective of what else is going on in the circuit. So if there's any change in RL, requires regulation. We refer to that process as load regulation, meaning the load is changing and the Zener diode must maintain VZ constant. And changes in VS, the supply voltage, or the power line coming from the supply, is known as line regulation. Okay, so Zener diode must work for both line as well as load regulation. And now you can see how things are affected, right? If V in increases, If Vin increases, then the supply current increases. If supply current increases, then IL and IZ would both increase correspondingly, right? But the first rule of a voltage regulator is the voltage must be constant. So if VZ is constant at the output, then the only thing that can change is IZ. Again, let's look at this first condition. Total supply current is the sum of the Zener current and the load current. If voltage Vs increases, that means the supply current Is also increases. If supply current Is increases, then Iz and IL should also increase. But the output voltage Vz remains constant. In order for that to remain constant, IL must remain constant. And if IL is constant, what happens to Iz? It goes up. So as Vs increases, Iz also increases in order for this rule to be maintained, or in order for regulation to be maintained. If Iz increases, the Zener diode must be capable of sinking a large amount of current through itself. And that's where the maximum power rating for a Zener diode comes into the play, or comes into the picture. So if Vs increases, then Iz also increases. Therefore, there's a max limit on the voltage supply. Constrained by PZ max, the maximum power dissipation of the Zener diode. Okay. And therefore, Vs has a max limit. Okay, that's why there's a maximum limit on the input voltage that you can apply to a Zener diode. Make sense thus far? Yes, question? Okay. All right, so now let's see what happens if the load changes, load regulation. So if RL increases, what happens to its current? IL. Ohm's law. Then IL decreases, right? Load resistance increases, voltage remains constant, V equals IR, right? And the other third quantity must increase or decrease depending on our application. So in this case, it would decrease. So if IL decreases, then IZ again must increase. So again, that's where PZ, power rating, maximum power rating of the Zener diode, comes into the picture, or as part of the design. Okay. So again, max value of RL is constrained by PZ max, power dissipation rating of the Zener diode. Make sense? All right, let's take a pause. Let me know if you have any questions. So far, so good. Okay. All right. Now let's see what happens if RL is too small. So if RL decreases, IL would increase. Okay. If RL decreases, voltage remains constant, VZ, then IL would automatically increase. If IL increases, then the total supply current must also increase. Okay, if IL increases, it's demanding more current, more power from the voltage supply, from the voltage source. So Vs, let's say IL increases, and therefore Is demand is also increasing. Okay, but another thing happens. If a large amount of current is flowing through, that voltage drop, sorry, if not a large amount, if RL decreases, then the voltage drop corresponding might decrease. So the voltage drop across RL decreases, VL might be less than the turn-on voltage VZ. In that case, the Zener diode is not in the picture at all. So again, if RL decreases below a certain limit, IL decreases. Therefore, VL, the voltage across that load resistor, may be less than VZ. And Zener may not turn on. And therefore, there is a minimum value of RL. Okay, that's the other aspect. There's maximum value for RL and there's a minimum value for RL. Any one of these limits, if any one of these limits is crossed over, that's considered to be a worst case scenario. Right? Worst case scenario would be like approaching the maximum power dissipation of the Zener diode or approaching the maximum value of RL or minimum value of RL. Okay. So depending on the variable, we'd have different worst case scenarios. All right. Okay, let's look at an example. So we have a regulator circuit. Vs is given as 24 volts. Vz is 12 volts. That should be a subscript. Vz is 12 volts. Rs, the series resistance, is 50 ohms. Let's see, 24, 50, and Vz or VL is 12 volts. Okay. Load resistance, RL, is 250 ohms, 250. And we are asked to find the maximum power dissipation for the Zener diode under worst case conditions. Okay, worst case conditions. So it's asking us for the maximum power dissipation of the Zener diode. What is the worst case scenario? The worst case scenario would be that the Zener current is going to maximum. If the Zener current is going to maximum, that means that the IL, load current, is at a minimum. If IL is at a minimum, that means a large value for load resistance RL. And so that's where we need to begin our analysis, or that's where we begin our design problem. Okay. All right. Let's wait for a few seconds. All right, so worst case scenario, right? Again, we are required to determine the maximum power dissipation, meaning PZ max. PZ max. For PZ max to occur, IZ must be at its maximum value. So we need to find IZ max. IZ max will occur when IL is minimum. Okay. IZ max occurs when IL is minimum. The load current on the right. I or IL. Worst case, what is the value of IL? How low can it go? 0. What is the value of the resistance for zero current? Infinity, meaning there is no load connected at the output. That is the worst case scenario for this regulator. Infinity. That means no load connected at the output. Okay. All right, so let's start at the top. We have IS coming this way. We have our KCL equation. IS is IZ plus IL. We can find IS because we have VS, we have VZ, and we have RS. We have all three values. So we can find IS from VS minus VZ over R. VS is 24 volts, VZ is 12, and RS is 50. This comes out to be 0.24 amps. Total supply current is dependent on RS, comes out to be 0.24 amps. All right. Now R, or the load resistor, is given to us as 250 ohms. So we can find the load current IL as VZ or RL. VZ is 12 volts, RL is 250. And so we have 0.192 amps. Oh, sorry, not 0.192, 0.48. 0.048. 0.048. 0.24 divided by 5. All right, or 48 milliamps. Once we have these two values, we can find the value for IZ. IZ on the first equation is IS minus IL. This comes out to be 0.192 amps. Okay, 0.192. So under these conditions, where the load resistance is 250 ohms, we can find a value for IZ. IZ would be 0.192 amps. And from this value, we can also find the power dissipation. Okay, so the power dissipation for a 250 ohm load, PZ is VZ times IZ, 12 times 0.192. This comes out to be 2.304 watts. All right, let's take a pause. Let me know if you have any questions. All right, so now we plug in the worst case scenario. What's this worst case scenario means? IL is equal to 0. So IZ would be equal to IS, which would be equal to 0.24 amps, meaning all of the current is going through the Zener diode, 0.24 amps. And now if we find the power rating for this, that should give us the maximum power dissipation. 0.24 times 12 gives us 2.88 watts. So maximum power dissipation in the Zener diode is 2.88 watts when no load is connected. All right, go through the steps and let me know if you have any questions. No questions? Okay. All right, design problem number 2. We have a Zener diode, we have load resistor R. We are not given the values for R. That's actually the question. We need to find RL. All right, let's just use R minimum and R maximum. That's the load resistor R. So find the range of values for which the Zener diode would still work as a voltage regulator. So we are performing or designing for load regulation. Vs is constant at 50 volts. Vz is constant at 14 volts. Maximum power dissipation for the Zener diode is given as 5 watts. Series resistance is 20 ohms. There's also a 10 ohm resistor just to indicate resistance of the power supply. Typically, power supplies will not have this higher resistance. But for our analysis purposes, it does not actually matter. We can simply write RS series resistance is 10 plus 20 and say it's 30 ohms. Okay, for the purposes of analysis, it does not matter. We'll simply add it onto the series resistance. All right. So R minimum and R maximum. If load resistor R is at its minimum value, what happens to its current? Current increases. The current would be its maximum allowable limit. So I would be at max. And let's just call this IL, IZ, and IS coming from the supply. Right? Standard KCL, IS is equal to IL plus IZ. So in order to find the minimum value of the load resistor, we need to work with the maximum value of the load current. Maximum value of the load current would mean, if you take that KCL into account, that Zener current is equal to 0. Okay, Zener current is equal to 0. Again, from our KCL, IS is equal to IZ plus IL. So maximum value of IL for a given value of IS can only be possible when IZ is equal to 0. So at that point, we can write IL is simply equal to IS. load current is equal to the total supply current. All of the current coming from the supply is going through the load. Okay. So we can find our minimum as your output voltage Vz over Is. Vz remains constant. Is would be its maximum value, and that would give us the minimum value of load resistor R. Is can be found from the equation Vs minus Vz over Rs. 50 volts and a 14-volt Zener with a 30 ohm series resistor gives us a value of 1.2 amps. 1.2 amps. So our minimum is Vz 14 divided by 1.2, and this comes out to be 7.6667 ohms. It's the minimum value of R. I'm taking 4 decimal places just to illustrate a point. Okay. Oftentimes in the lab, when you're performing, our answers are not exactly the same as the theoretical calculations. Sometimes they're in the ballpark, sometimes they're like very far off. Okay. So if we calculate this 11.667, we say, okay, let's say 11.67 or 11.7 ohms, right? If you try to build this in the lab, there's no resistor with an exact value of 11.7. We have to create it with a combination of series and parallel resistances. And so depending on how close we can get to that value, our answers would be either close or far away from our calculations. Anyway, that was just a small point. Okay, that was for R min. If you want to find the maximum value of R max, what happens to current? This is max IL. IL must be its minimum, right? IL is minimum. That means we are looking for a case where IZ goes maximum. Right? Where IC goes maximum. And we already know what the maximum current handling capability is because we are given the Zener diode voltage and we are given the maximum power rating. So we can find IZ max from PZ and VZ. PZ is 5 watts and VZ is 14. Gives me 0.357142 amps. Okay. This value for IS is also the maximum value that is allowed in the circuit or permitted in the circuit. So IS max is 1.2 amps. So IL min will occur when there's maximum supply current and there's maximum Zener current, leaving only a small bit to go to that load. Right? Make sense? Therefore, IL min is IS max minus IZ max . is equal to 0.842 85858 858 amps. Now that we have IL min, we can directly calculate R max. R max, maximum value of RL, the load resistor, VZ or IL max. (16.61 ohms). So a circuit would work as a voltage regulator, or the Zener diode will work as a voltage regulator only for load resistors between 11.67 and 16.61 ohms. Very small range. If your load resistor is outside of these ranges, it will not work. All right, let's take a pause. You write it down, think over it. Let me know if you have any questions. Keep in mind, again, we are only looking at like 2 examples with like 3 different considerations, but there are, depending on the variables and depending on the question being asked, it could be a combination of any of these variables. So there's multiple case scenarios when you're trying to design a circuit. Any questions? Did it all make sense? At least upon review outside of class, right? Okay. All right, let's see how much time we have left. 148. Last 2 applications of diodes. So diodes are used as wave shaping circuits. One of the most common examples for a diode circuit is clipper and clamper. Diode clippers, again, we saw peak detectors, high wave rectifiers. Clippers also work the exact same functionality. The only difference is instead of taking the output across a resistor, the diode is not in series with the power supply, it's in parallel with the power supply. So our diodes are right here. Let me analyze this with a, let's say, a simple circuit first. So we have a circuit where we connect a diode this way. And there's our output load resistor. Okay. And let's just, for simplicity's sake, let's apply a sine wave. Okay, we are applying a sine wave. So there's a sine wave going in. Let's do this. So this is V in. What do you think is V out? Let's use ideal diode model. Positive half cycle. What happens to diode D1? Is it on or off? Right, it's on. So ideal diode model, positive half cycle, diode is on. Plus minus resistor short circuit. So what is V out? Show of hands for 0. That's it. Show of hands for V in. Show of hands for dead circuit. V out be equal to 0 because this is the exact same node. If you have a wire between two nodes, they're the exact same node. It's the exact same node, then the voltage, then the difference in electric potential is 0. So V out is 0. So V out goes to 0. Negative half cycle, what happens? Diode is reverse bias. It's open. V out is equal to V in. So the positive half cycle is clipped. We do not obtain it at the output. Again, in a half-wave rectifier, the diode was in series with the supply. In these circuits, we are simply taking the diode, the output across the diode itself. Okay. So positive half cycle is clipped, and we only obtain negative at the output. So positive half is chopped off or is clipped. Same thing happens when you have the diode in the opposite direction. So this would be a positive clipper because it's clipping the positive half cycle. And this would be negative clipper. Which is when we have diode connected the other way. And again, you can perform a self-analysis on this for practice. Just draw the two diagrams and you're able to see it clips off the negative half cycle. Okay. All right. So ideal diode doesn't require any voltage, does not drop any voltage across itself, simply clips off. If you use a practical diode, it requires 0.6 volts to turn on. So if we take the same circuit, but we use VD as 0.6 volts, the offset diode model, a small positive voltage turns. The diode is off until the input crosses 0.6 volts. And so you get 0.6 volts at the output in the positive half cycle. Okay, positive half cycle. So diode requires 0.6 volts to turn on. Now, instead of 0.6 volts, you connect a battery as shown in this circuit. If you connect a battery or a DC voltage source, then the cathode of the diode is held at a higher potential. So depending on the value of this battery, let's say this battery was 1 volt, for instance, then the anode of the diode must be larger than 1 volt in order for that diode to turn on. But once it turns on, once the diode turns on, V out is equal to the battery. Okay, so the waveform would look like this. So you can change how much of the waveform you want to clip depending on the value of the battery. Yes. So it's a sine wave that gets chopped off. That's what it looks like. Question being asked is it like an actual trapezoid? So it's not quite, because it's following the sine wave function. So it's not quite a straight line. Okay. Now the thing to keep in mind is this portion, like right here, up to that point, the voltage is coming from the V in. And again, this portion right here is coming from V in. This is coming from the battery. Once V in crosses the level of the battery or the DC source, that input goes directly to the battery and back. So it completes the circle. It completes this circuit pathway. And the output only sees the battery, doesn't see anything else. Okay. So that middle portion in there comes from the battery. So this portion is said to be flipped. Okay. I know we are in a rush. It's about 3 or 4 minutes left. So I want to get to the next circuit, which is the clamper circuit. Clampers require a capacitor, energy storage element. This is a simple clamper circuit. There are multiple kinds of clamper circuits depending on the direction of the diode, depending on the capacitor polarity and the pathway where it's connected. So let's say we have a, again, simple sine wave applied. And let's say this sine wave is Vp. This is minus Vp. Diode turns on in the positive half cycle. When it turns on, capacitor charges. So there's a pathway for the current to flow through. The capacitor charges is going to store energy in with this polarity. Plus minus. This is the positive half cycle. Okay. Positive half cycle, diode is forward biased because the diode is connected with the anode towards the positive end. Behaves like a short circuit, capacitor charges. The maximum value on the capacitor is Vp. So once it's fully charged, Vc is equal to Vp, maximum value of the input. Now, in the negative half cycle, I'm going to omit that resistor. This is, well, this is minus Vp, but I've already flipped the terminals anyway. And you have a capacitor, fully charged capacitor that behaves like a DC source, right? You have Vp here. Okay. Now, when you take the output across the resistor sees the capacitor and the negative half cycle in series. If you apply KVL with this diode direction, the waveform has now shifted down. So V out is equal to minus Vc plus Vp. And so V out will be an exact replica of the sinusoidal input, but it will be shifted down by an amount of Vp. So let's say Vp was that. It'll be original Vp was there. Output would be somewhere here. Let's say original Vp was here. Now it's shifted down by Vp. So now it's clamped to a negative level. If we flip the direction of the diode, we get a positive clamper, meaning it's clamped up because the capacitor charges in the opposite direction. And that's clippers and clamper circuits, two of the diode wave shaping circuits. Yes. Yes, so there's a transient portion, assuming you study transients in 215. Transient analysis, yes, no. Capacitors and inductors are energy storage devices. They receive energy, they store it in electric fields or magnetic fields, and they release it back into the circuit at a later point in time. That's what's happening. But you cannot snap and have an instant charge. So it ramps up. There's a transient portion. So by the time it goes from 0 to full, that's the transient analysis. But eventually it reaches the full charge. Once it reaches full charge, then we obtain a waveform like this. But if you perform this circuit in real life, it's like really fast. Depending on the frequency of the waveform, it will take like microseconds, right? You flip a switch on, and instantly you'll see a clamped waveform. Okay. So clippers and clampers, those are two of the most common applications for a diode, using diodes. There are other circuits and a few other slides after this. So it's further learning. If students want to explore further, you can do so. It's already there in the book. But for now, for today, I'm going to say chapter 3 is at an end, and we'll go back to BJTs from Friday onwards. Okay. There is a reading assignment, I believe, based on, there was photodiodes and light emitting diodes. Okay, I'll cover this on Friday. Just one last slide. And then we'll go into BJTs. Okay.